I am absolutely thrilled to have you here. Today, we're throwing on our hard hats and getting into the real fundamental backbone of electrical safety, earthing systems. We're going to dig into the standards and really unpack how the principles of grounding are the exact things that determine whether a fault safely dissipates into the earth or turns into a totally catastrophic hazard. Let's get right to it.
Okay, let's dive into this. We've got a lot of ground to cover, literally. Here's our roadmap. First, earthing fundamentals and standards. Then, soil resistivity testing methods, followed by earth resistance measurement techniques. After that, we'll hit grid integrity and hazard potentials, tower footing and site challenges, and we'll wrap up with safety practices and compliance.
Section 1, Earthing Fundamentals and Standards. Any good field manual has to start with clear definitions, right?
So think of an earth electrode kind of like an emergency exit for electricity. Our sources define it quite simply. It's a conductive part intentionally connected to the general mass of the earth, and its primary job? To provide a reliable, low-impedance path for fault current to safely leave the installation and get back to the source. It is all about protective equipotential bonding. By connecting non-current-carrying metalworks to this earth, we limit their potential during a fault, which is exactly what prevents dangerous, life-threatening shocks.
Now, here's where things get serious. This isn't just best practice anymore, guys. It's the law. The Central Electricity Authority's 2023 regulations have drastically shifted the landscape here in India. As this regulation highlights, compliance with IS 3043 is a strict, mandatory requirement. The focus has completely moved away from just trying to hit some arbitrary low resistance value, like blindly aiming for a generic 1 ohm. Instead, the law now demands rigorous safety analysis to genuinely ensure human safety under fault conditions. To actually achieve that compliance, IS 3043 classifies earthing into a few specific architectures, and knowing exactly what system you're working with dictates your entire testing methodology. We have the TN system, where the source neutral is earthed and exposed parts connect back to that source earth. Then there's the TT system, literally terra-terra, or earth-to-earth, where your equipment relies on its very own local independent earth electrode. And finally, the IT system, which is completely unearthed or earthed through high impedance. If you don't know which one of these you're testing before you start, your readings are basically going to be meaningless.
Moving on to Section 2, Soil Resistivity Testing Methods.
Now, what's really interesting about the pre-design phase is that before we even think about engineering a ground grid, we have to measure the earth itself. The Wenner 4-point setup is universally recognized as the absolute most accurate technique for this job. You drive 4 equally spaced probes into the ground in a straight line. Then, an instrument injects a known test current through the 2 outer stakes and measures the resulting voltage drop across the 2 inner stakes. It's a really elegant, highly effective way to scan the different layers of the earth. Okay, I know, it's a formula, but stick with me, because this comes straight from IEEE 81 and IS 3043 Clause 40. Resistivity, or ρ, equals 2 times pi times A, which is the spacing between your probes, times R, the measured resistance. But the absolutely crucial field rule here is that the depth of your probes, our H variable, must be less than or equal to 10% of the spacing. It prevents skewed data. So if your probes are 10 feet apart, they absolutely shouldn't be driven deeper than 1 foot. That ensures the formula accurately translates your resistance reading into the true soil resistivity. But hey, what happens when you need to scan way deeper into the soil? Well, you increase the spacing. The catch is, with the Wenner arrangement, as spacing gets very large, the potential reading between those inner electrodes drops rapidly. Oftentimes, commercial instruments just struggle to pick up those tiny values. That is exactly where IEEE 81 suggests switching to the Schlumberger-Palmer arrangement. By keeping the inner potential probes closer to the outer current electrodes, you artificially boost the voltage signal, entirely overcoming the limitations of your meter over those massive distances. Pretty clever, right? All right, Section 3, Earth Resistance Measurement Techniques. Let's fast forward a bit. The grid is physically in the ground, and it is commissioning time. The fall of potential method, also known as the 3-point test, is the gold standard here. You pass a current between the earth electrode you're testing and a remote temporary current spike. Then, you use a third potential spike placed somewhere between them to measure the voltage drop. By moving that potential spike away from the test electrode in measured steps, you can literally plot a curve of apparent resistance. Now, finding the true resistance on that curve means you have to avoid the spheres of influence of both the test electrode and that return current spike. So the crucial point is we use what feels like a magic number, the 62% rule.
You place your potential probe at exactly 61.8% of the total distance to the current probe. You record that reading, but, and this is key, you do not stop there. You verify its accuracy by moving the probe to the 52% mark and then again to the 72% mark. If those three readings are fairly consistent and level, boom, you've hit the flat plateau of the curve and your measurement is solidly valid. Look, the real world rarely hands you a perfectly flat, wide-open field, right? For a new large substation, fall of potential is highly accurate, sure, but it requires massive space and full system disconnection. What if you're in a heavily paved urban area? You might opt for the clamp-on stakeless method. It's incredibly fast and non-invasive, but remember, it literally only works on multi-grounded systems where a parallel return path actually exists. The two-point dead earth method is another fallback, using a known good ground like a municipal water pipe. But it's much less accurate because it lumps in the resistance of the return path itself. You really have to select your method based on the reality of your site.
Which brings us to Section 4, Grid Integrity and Hazard Potentials. So, according to IS 3043, Clause 10, and IEEE 80, our primary design criteria aren't just ohms, they are hazard limits. Touch voltage is the potential difference between a ground and metallic structure a person is touching and the earth right under their feet. Step voltage is the potential difference between a person's 2 feet on the ground during a fault. And earth potential rise, or EPR, is how high the voltage of the entire grid jumps relative to remote earth. Modern compliance is all about ensuring these specific potentials stay strictly within safe human thresholds during an active fault. To keep those potentials in the safe zone, the copper grid beneath the substation must be perfectly intact. But think about it. The ground grid forms the backbone of the system, and it generally lies about 600 millimeters below the surface. You can't just dig up an entire live substation to check for a rusty wire. That is exactly where ground grid integrity testing comes in. By using advanced, non-intrusive, high-current injections between different risers above ground, we can evaluate the hidden grid below. It identifies dangerous breaks, underground corrosion, or weak connections without picking up a single shovel. Moving into Section 5, Tower footing and site challenges. And this brilliantly illustrates one of our biggest field headaches, testing transmission towers. Normally, transmission towers are all connected to one another by an overhead static ground wire. If you just hook up a standard tester to one leg, you aren't just testing that one tower, you're testing the entire transmission line. But specialized high-frequency meters use neutralizing circuits to electrically isolate the tower you are standing at, totally eliminating the need for you to physically climb up there and disconnect the static wire. It perfectly solves what we call the parallel path problem. If you use a regular low-frequency tester, it gives you a falsely low reading because the signal just travels straight down the overhead wires to adjacent towers. High-frequency testing, on the other hand, mimics the high-frequency nature of a real lightning strike. A lightning strike happens so incredibly fast that the affected tower acts as if it's electrically isolated anyway. Measuring the true isolated footing resistance gives utilities the exact, accurate data they need for optimum lightning protection design. Finally, Section 6, Safety Practices and Compliance. Listen, the absolute #1 priority for any of us out in the field is getting home safe. Standard IEEE 81 Section 1.2 states it perfectly. Testing live electrical systems is inherently dangerous. There is no way around it. You are dealing with potential fault currents, transient surges, and severe electrical shock risks. Simply pushing test currents into the ground can create potential gradients that might harm you, your crew, or even interfere with neighboring facilities. Proper PPE, strict adherence to procedures, and constant situational awareness are totally non-negotiable. Which leaves us with this final, honestly pretty critical thought. The engineering standards in India have evolved dramatically from simple resistance checks to comprehensive, legally binding safety audits. So, I have to challenge you. Take a hard look at your current site practices. Does your testing protocol fully comply with the rigorous new CEA 2023 regulations and the latest IS 343 revisions? If the answer is no, it's time to upgrade your field manual. Thank you so much for joining this explainer. Stay safe out there and keep your ground solid.